Good morning, good evening, good afternoon. I'm Paul Trust, and I'll be taking you through today Bayesian methods for big data, a variational approach. But today we shall basically look at the background on Bayesian methods. So as a primer, Bayesian methods come from a field of statistics called Bayesian statistics. And this field has been here for very many years. But it's gaining attention of recent days because of its usefulness in powering most modern machine learning methods. So our roadmap today will be why Bayesian? Why should you go Bayesian? I will take you through the Bayesian pipeline, the computational challenges, variational bias, a mean field variational bias, summary, and conclusion. We may not be able to cover everything today in this lecture, but this is the roadmap on what we shall cover throughout the course on the variation approach. So why Bayesian methods? So if you've been following through machine learning and data science, you will realize that there are important models like topic models. There is one like that was proposed by David Bay, latent dielectric allocation. It is used to analyze large collections of documents. And what actually powers that method is what we call variational inference. And variational inference is a class of Bayesian models. So if you're motivated in analyzing large corpora, that's you need the knowledge of Bayesian inference. So they are missions which require a lot of uncertainty. If you know, like the search mission of the MH370, most of the promising methods that are being used involve Bayesian methods because it involves a lot of uncertainty. Artificial intelligence. As I had said, most of the topics in artificial intelligence, especially a class of models known as generative methods, they are powered specifically by the theory of Bayesian methods. When you talk of models like variation autoencoders and very many latent variable models, these are a subclass that actually apply Bayesian methods. When you look at causal inference, it's a very important area, but most of the methods there borrow from the statistical inference of Bayesian statistics. Clinical trials, because clinical trials normally use Bayesian methods rather than the traditional statistical inference of frequencies, as we shall see, because Bayesian inference does not only give point estimates. For example, you find it will give also the uncertainty around point estimates, as we shall see more in this lecture. So there are various softwares that you can use. There is Stan, there is Python, there is a lot of them, as we shall see as the course goes on. So Bayesian, by the way, has not started in this century. From one of the best statisticians, there is this powerful article you could find interest in reading. So one of the top statisticians predicted that actually in the 20th century, Bayesian would overtake frequentist view. As some of you may not know the difference, I will just come down there to explain what's the difference between frequentist and Bayesian. But he actually predicted that in the 20th century, everyone would be Bayesian. But we are in the 21st and not everyone is Bayesian. And he's explaining why isn't everyone Bayesian. This is an interesting article, and we shall explain why you should not be solely Bayesian, why you should learn both of the sides of frequentist and Bayesian in order to, when faced with a problem, in order to choose which kind of methodology to choose. So what I am trying to say here is that I'm not teaching an alternative view. I'm just giving you something complementary to the tools that you may have in your statistical box once attacked by a problem which you could use. So to understand Bayesian statistics, you need to look at it from two angles. One is probability. How do we define probability? So historically, there are very many definitions of probability, but I find two probabilities important. One is the frequentist view of probability, and the other one is the Bayesian view of probability. So these are the most important definitions of probability that have two different views that traditionally have two competing views. And many people have chosen to be frequentist and others have chosen to be Bayesian. So most of you and most of us, when we are taking undergraduate classes, and most of the graduate classes, they are taught statistical inference based on the frequentist probability. So basically, the frequentist interpretation of probability is that the average proportion of an event will occur if a trial is repeated infinitely many times. So imagine if you want to know the average age of students in a class. According to the frequentist point of view, it is sufficient to collect as many ages of people in a class, and you take the average. That average will tell you the average age of people in a certain class. If you want to know about a certain parameter of interest you don't know, it is sufficient to go and you collect as many samples as possible, and then you average them. So the idea behind this frequentist point of view is that if you collect infinitely many samples, this parameter will actually approximate the true parameter you don't know. Because why we go to statistics is because we don't know what you may call the population interests. So this is an advanced course. We assume that this knowledge is known, but to tell you in statistics, there is what we call a sample and a population. So when you have a population, that means you know all items of interest. You don't need to do statistical inference. You just go and get the true statistics. But because it's not normally possible to enumerate everyone in the population, we go to do sample statistics. So we use the sample to approximate the true population. So what this frequentist probability is, if you collect as many samples as possible drawn from the population, the average will actually approximate the true population parameter. So that's the idea. So there is what you may call Bayesian probability. So Bayesian probability takes a different view. So Bayesian probability is what you may call the subjective belief that an event will occur in presence of incomplete information. So Bayesian probability doesn't look at the probability as long-range frequency, because the argument here is that if you don't have information about the population, the parameter of interest, it doesn't matter how much samples you have. If you don't have information in those samples corrected, still you will not get information. So you'll find that according to Bayesian probability, there is no such a thing as probability of an event. You see, Bayesian probability, frequentist probability would say the probability of having a girl child is this. So according to Bayesian probability, there is no probability of an event. And why is it so? It's because according to Bayesian probability, your belief, that's why we are saying it's on subjective belief. Your belief updates as information arrives. Imagine if I don't know the mass maybe of an alpha, I don't know it, I don't know any mass. But if you give me some information that, for example, an elephant is bigger than a cow. So I may, since I know a cow, I will say, oh, so that means an elephant could be at least 100 kilograms. But if you give me some more information that actually an elephant is twice a cow, then I keep updating information. So there is no probability of uneven. This probability continuously changes as information arrives. So it's, you could think as Bayesian probability as being inherently subjective in that it depends on the believer's information. So different observers will have different views about something depending on the information they have. There is, for example, the prevalence of coronavirus, COVID-19. If we want to know the prevalence of a virus in a certain area, and we have not done statistics, so if you ask two different people, they will have different views depending on the information they have. Imagine you thought it is 10%, but they told you that last week or yesterday you didn't have information that there was an outbreak of extra 1 million cases. So for you, you'll have the information of the previous day. So Bayesian probability interpretation is the subjective belief that an event will occur in the presence of incomplete information. So information is very, very key in Bayesian probability. So when we are talking about Bayesian and frequencies, there is one key thing of interest, the parameter of interest. These parameters of interest would be what you may call mean. It would be the variance. It would be the confidence interval. It would be whatever you want to correct from your data you want. So when we go to do surveys, when we go to do research, there is a certain parameter of interest we are interested in. And this is how these two view parameter of interest. These parameters of interest, as I've told you, think of it as the mean. Think of it as the variance. You go to correct edges, you want to know the average edge. So the frequentist probability, this diagram summarizes it all. The frequentist probability interpret the parameter as fixed. We assume that if I want to know the average age of students, like in this class, we know that it's one fixed parameter, even though I don't know it, but it's one. So long as if I enumerate the whole population, I will get that one fixed parameter. So that means that parameter doesn't change, it's one. So the idea is it's the data that changes, but there is one fixed parameter that generates the data. So we want to produce a procedure that actually can interpret our world. We want to get a methodology that can estimate this population parameter of interest. But according to Bayesian statistics, there are very many parameters depending on the knowledge you have. So every expert has a different view of the parameters of, it has a different view of the parameter of interest, depending on the prior information. So you realize that in Bayesian statistics, one key thing that will differentiate them is the use of prior knowledge. And imagine prior knowledge could be, if you're trying to test someone like for COVID, you need to know what's the prevalence of COVID in that area. That is the prior knowledge you have. For example, if a disease is rare in an area, even if a test is positive on a person, imagine there is a disease which is 1 in a million, and somebody, your test gives him as a positive of that disease. How worried should they be? Because if the disease is 1 in a million, you may find that much as your test is 99% accurate, his chances of actually having the disease is less because this disease is rare. So the Bayesian view of probability, there is a certain prior you come with before attacking a problem. There is a prior knowledge. I come with a certain prior knowledge. For example, I know that from previous studies, the proportion of people who have HIV in this area is this. The proportion of people who have a certain disease is this. The proportion of people who have passed this interview is this. So I come with that prior knowledge before estimating the parameter. So after observing the knowledge, after observing the data, I update my prior beliefs. So that means, but why are these very many? Each observer will have different beliefs depending on his prior knowledge. So you will find that there are many parallel in the Bayesian world. There are many parallel worlds taking different parameters, theta. So we are placed in one parallel world randomly, and we believe that we are in the theta world with a probability of theta. So each expert will have a different parameter initially depending on his knowledge, unlike the frequentist point of view, where there is one fixed parameter regardless of your knowledge. And that creates a point of divergence between frequentist and Bayesian with regards to the parameter of interest. Here we're using prior knowledge. Here we are not. This use of prior knowledge is one criticism of Bayesian statistics, and it's also one of its key strengths, because many people from the statistical world, from the frequentists, ask, how do you define the prior? Because also this ambiguity, the prior varies depending on the believer's information. But what I can say as an expert in this area, when there is incomplete information or when there is less data, you find that the use of prior information actually helps. Even if the information is actually weak, like subjectively weak, you find that it helps than having no information at all. So to understand this area, there are two basic laws you need to know from probability theory. So one of them is the conditional distribution. So in probability theory, conditional distribution is a ratio of joint distribution over marginal. So in probability theory, if you say probability of X given Y, it would be the joint of X and Y over the probability of Y. And one other key rule you need to know is the product rule. Any joint distribution can be expressed as a product of one-dimensional conditional distributions. You can look at the joint distribution as probability of X given Y times probability of Y, which is also equal to probability of Y given X times probability of X. So these are very simple probability laws, but these are the laws that actually power what we may call Bayesian inference, because from these two laws, we shall derive what you may call as the Bayesian rule. And it's from the Bayesian rule that actually most of the things flow. So there is also the sum rule, where if you have any marginal distribution, it can be obtained from the joint distribution by integrating unnecessary variables. And this is for continuous variables. If you want from the joint P of X given Y, if you want only the probability of Y, you just get the joint probability of X, Y, and you integrate over X. Maybe integration may be new for you. So this is also holds for discrete variables, where instead of integration, you can think of the sum. So in other words, if you have two variables, the simpler way of getting one out of the two variables is to sum out the other variable. Integration is the sum. And of course, we already saw that probability of X given Y is probability of Y given X, probability of dx. And this one can be seen as an expectation of P of Y of X. You remember expectation you remember that expectation of x is equal to the integral of x, p of x, dx. Yeah, dx, I don't have my pen. So that's all, it's the summation. So this is where this one is, we are deriving this from. So yeah, so that's it. So from these two basic probability, there comes a very important law by Thomas Bayes. By the way, this first work first appeared in Thomas Bayes. This was a very critical, important work. It was published in his paper. He actually died before they actually looked at this important theorem. Initially, because there was a problem on how to define the prior information, people like Laplace came out with what you may call the frequency view of probability, because the subjective belief that was proposed in Bayesian inference, that subjectivity faced a lot of criticisms, and other scholars like Laplace, like Wald started working on an alternative view, which came out to be the frequency point of view. So Bayesian looked at these two laws of probability and derived what you may call as the Bayesian theorem. So Bayesian theorem just is derived from product and sum rules from the product. By looking at, you can get a joint probability by just factorizing out these variables, and you can also get the marginal by integrating out the other variable of not interest. So from this, he derived what you may call the Bayesian theorem. This Bayesian theorem is one of the most important theorems to know in Bayesian machine learning, Bayesian statistics. It is so important, but yet it is such simple. First introduced by Thomas Bayes, but then it has been extended from then in the 17th and the 16th century. So it says that the probability of theta given x is probability of x given theta times probability of theta over probability of x. You realize that it's the same as this. Probability of x given y is probability of x given. You realize that it's the same as this. Probability of x given y equals probability of x given y over probability of x, y. So this is, now we are just putting theta given x, it's probability of x given theta, probability of theta over probability of x. So in the language of probability, this is what you may call as the likelihood. This may call as prior. This is what you may call as the evidence, and this is what you may call as the posterior. So these are very important. So the likelihood is basically looks at how likely our parameters have been generated from the data. So you will realize that frequentists, if I'm to talk from the statistics point of view, frequentists that disregard prior information. They only value data. That's why you see like the most important, one of the most important methodologies used in frequentists is called maximum likelihood estimation, MLE, which is used to power methods like the logistic regression, your neural networks. Most of the methods are actually powered by maximum likelihood. But maximum likelihood has its flaws, as I will show. So as the course goes, but they only look at data. But what about prior information? what about prior information? So what Bayesian methods do, they look not only at the likelihood, but also on prior information. Prior information, as I said, is information you have at hand. As we proceed, like in advanced machine learning courses, you will find how prior information is important. There is like a method that is actually powering most of the modern machine learning methods, like what you may look at as transfer learning, where they first train a model on large corpora and use it, fine-tune it on small data sets. That one tells you that actually they're using prior information learned on a previous task. That's one, and that alone method of what you may call as pre-training has actually drove significant performance gains in most of the models, because people don't need to access large corpora. You just need to get a model and access its prior information. Systematically, they don't use Bayesian inference, but I am just trying to tell you, since you did courses in machine learning, I'm just trying to tell you how significant prior information is. So this is what we may call as the posterior distribution, likelihood, prior, and evidence. You'll see a lot of this P of X. Some people call it as evidence or model evidence. And you'll find, we shall come to find that this is one of the key problems in Bayesian methods. So if you can see, you realize that P of X, if our parameter of interest is theta, P of X is independent of theta, so it's a constant. That means posterior is directly proportional to the likelihood times prior. So this would be sometimes a very important equation of interest C. So I want to just give a simple example of when Bayesian inference can be so important. So imagine you went to the hospital and they are testing you of cancer. You know, this is so hard. People fear of cancer and stuff like that. So we want to know if your test is, imagine you got a positive cancer test. How worried should you be? All of us don't want to die. And when people have cancer tests, they have that stigma, they think they will die, and yet there is chemotherapy and stuff like that. So we need to know, if you got a positive cancer test, how worried should you be actually? So you realize we've just had a result back from the doctor for a cancer screen, and it comes out back positive. How worried should we be, given that test is imperfect? We already know that we have a positive cancer test. How worried should we be, given the test is imperfect? So imagine that before the results came in, the chance of having this type of cancer was as low as 1 in 1,000. Imagine where you live, I don't know, whether India, whether Canada, whether in Africa, 1 in 1,000 people in where you live, this is of course so high still, have actually cancer. If we can let theta represent the parameter of us having cancer, that means before you take the test, the chance that you actually have cancer is 1 in 1,000. This is what you may think as prior information. Because in the village or country or continent or the world where you live, 1 in 1,000 people actually have cancer. So that means before even you went to the hospital, the chance that you have cancer was 1 in 1,000. It was 1 in 1,000. That is the chance. That's before you actually went to take the test. So this 1 in 1,000 actually means that if you went randomly in your country and you pick a person, the chance that you pick 1,000 people, the chance that one of them have cancer is 1 in 1,000. So, but we know that for people who do not have cancer, the test is 99.9% accurate. Wow. this test is amazingly accurate. If you don't have cancer, the chance that this test will actually test that will bring you a negative result is 99.9% accurate. When, oh, now I know this person testing is mad. If the test is this accurate, this is worrying. So this can be, if we denote the event of the test returning positive, imagine being as 1. So you can look at this as the probability of the test being, you remember theta is denoting, is the parameter denoting us having cancer or the other person having cancer. So this probability is if you do have cancer, the test is 99% accurate. So here, imagine that you have cancer and the test is positive. So that means test is positive given that you have cancer. In 1,000 tests, in 1,000 people, this is accurate for 991 people. We also have some other statistics. For people who do not have cancer, the test is 99% accurate. If you actually don't have cancer, the test is 99% accurate. The probability that the test returns a positive result, given that you do not have cancer, of course, we have to reverse this result. If you do not have cancer, the test is 99% accurate, but you know from the laws of probability that probability like of having cancer can think as probability of having cancer plus probability of not having cancer is 1. We know that from the laws of probability that the total probability is 1. So if for people who do not have cancer, the test is 99% accurate, so we are looking at the probability that the test is positive given that we do not have cancer. In other words, we are looking at the false positive. Because here we are worried, we already have a positive result. We want to know, is it actually a false positive? Because we are worried. So our point prospects might seem grim because our prospects might seem quite grim at this point, given how accurate the test is. Imagine it gives a false positive only 1 in 100. It gives a positive result in 99.9% of the tests it does. This is worrying, but Bayesian inference gives, but in reality, this doesn't happen that way. If you apply your, if you want to figure out the chance we have cancer properly, we may need to do this through Bayesian inference. What is the chance that we actually have cancer and the test is positive? We use Bayesian inference. From Bayesian inference, it follows that if you have theta given x, it is probability of x given theta times probability of theta over probability of x. So from here, it becomes probability of, from probability of theta equals to 1 given x equals to 1, becomes probability of x, just reverse this, x equals to 1, divide given theta equals to 1, probability of theta equals to 1 over this. But we calculated all of these probability of x given 1, given theta equals to 1, we already saw it, is 999 of 1,000 is that. Then probability of theta equals to 1, that was the prior, 1 out of 1,000, over probability of x equals to 1, this is the marginal distribution, and we saw that the marginal distribution is got from the sum or the integral, but here we are in discrete cases, so it's the integral. So you realize that after calculation, my point here is to show you that much as the cancer test is positive, our chance of actually having cancer is not 99. This is amazing, because from the test, you would think that since the test is 99.9% accurate, that our chance of having cancer if we receive a positive result is 99. That's what a frequentist person would say. In actual sense, it's not actually 99. It's 1 out of 11. And why is that so? It's because of the influence of prior information. Because where you live, there are few people who have less, who have actually cancer, very few. So a frequentist person thinking, he would think, oh, the test is 99.9% accurate. So I am 99.9% more likely to have cancer. Okay, likely to have cancer. But that's not true. You're around 0. Even if you got a positive test, the chance that you actually have cancer is less than 10%. That's how magic, how actually Bayesian does. Of course, but if you did a second test, I didn't show this example. If you did a second test and you actually receive a positive test again, your chances of having cancer will increase from 90, will increase from 10% to around 70 or 80%, because it will update information. It's less likely that the way this test is accurate, that it will make a mistake twice. So in other words, if you did a second test, this will be your prior information. Your prior information will no longer be 1 out of 1,000, because now we have some prior result on you. We have some results on it, and that's 1 out of 11. So you realize that this way of thinking from Bayesian thinking prevents us from extreme thinking. So another intuitive example I will end with is an example of a coin tossing. Imagine if most of us have a coin, and I will use the one from a certain country in Africa, from Uganda. So this coin may have a head or a tail. So we have a coin which may be fair or not, and the task is to estimate the probability of landing heads up. So assuming this coin is fair, you may be seeing this as a head, and this is a tail. So if this coin is fair, we may think that the probability of us having a head is 1 out of 2, because probability is 1 out of the total. And the probability of having a tail is 1 out of 2. 2 tries. Imagine we throw this coin, it's the same coin, we are throwing it up and seeing, do we observe a head or a tail? Imagine in 2 trials, we get 2 heads. What would the frequentist person say? The frequentist person will say, the probability of having a head is actually 1 out of 1. So that means if you're using this to inform policy, you would say that all coins, this means that all coins are biased towards heads. This is not true, because we have only done 2 trials. So the frequentist person will say the coin is not fair and always lands heads up. Can you imagine? The coin in 2 trials came out as 2 heads, and this is more likely even in 10 times. So from the frequentist point of view, he would conclude in all experiments, the coin landed up 1, and the coin is not fair. But what would the Bayesian think? The Bayesian thinking in 2 trials would think about the prior information. First of all, it would think about what's the prior. The prior in this case would be a half. What is the likelihood is what we have seen in the data. And then we would compute the posterior. and we would report the results and summary. So you would find that I drew the posterior of frequencies and the posterior of the prior, and you find that the posterior of Bayesian would actually be would not just be striking on one, it would be something left skewed, but not as one, because the frequentist would have its prior distribution at one, which is somehow misleading. So this is how you build a model. Look at your prior, look at what comes from the data, and look at, you report the posterior and summary statistics. So, but as you get more data, you realize that the coin, of course, is not always biased. So when this experiment, I did it with more data in 1,000 tries, there were 489 tries and 511 heads. So you realize that as you get more data, both of the frameworks will agree that the coin is fair. So, I will stop here. But what I can tell you is that I will stop here for today, but the course is moving. Just for the interest of time, I'll stop. But what I will tell you, this is the Bayesian pipeline. You build a model, choose prior and likelihood, compute the posterior, and report the summary statistics. So in summary, what you should take home is that Bayesian statistics is derived from Bayesian theorem, and this theorem incorporates prior information. And one other things you should know is this Bayesian theorem is how to use the prior information. Then you need to know how these two view the probability of interest. One looks at it as a subjective belief, and one looks at it as a long-range frequency. And we shall look more how this Bayesian inference can be applied in most important models like the latent dielectric allocation. We shall look at it how it powers most modern artificial intelligence methods, especially those from machine learning, like variational encoders, which uses variational inference, a method in Bayesian statistics. Then we shall also look at how computing this P of X is somehow hard because of the integration that is involved, that will lead to other methods like Monte Carlo, Markov chain, Monte Carlo, variational inference, Laplace allocation, Laplace approximation, and very many others. So for today, thanks for attending and see you next time.